So in this final video, I'll cover computing reachability probabilities for MDP. So this is both minimum and maximum reachability probabilities. So there's several different approaches. So I'll cover value iteration, which is a approximate method, and it is an iterative solution method, and it corresponds to a fixed point computation, as we'll see. And this is preferable in practice, for example, as it's used in Prism. And I'll show you a second approach, which is a reduction to a linear programming problem. And then we can solve with linear optimization techniques. And this has a better complexity, although it's not better in practice. And it's good for small examples, and it also gives precise results, as opposed to value iteration, which is only gives approximate answers. And I'll also mention a third method, which is policy iteration. So let's first consider value iteration, and let's consider when we're computing minimum probabilities. So this can be computed as the limit. So here we're computing the probabilities for all states at the same time. So the probability, the minimum probability for state S of reaching T is the limit of these over N. So let's look at the case for state S. What's the nth value? Well, it's 1 if it's in the target, as we've already, as if we're in the target, then the probability has to be 1 either for both for minimum and maximum. It's 0 if we can't get there with probability strictly greater than 0, and I showed you how to compute this set in the previous video. And then if n is equal to 0, then we start from 0, and if n is greater than 0, then we base it on the values in other states. So we take the minimum, as we're computing a minimum probability over the available actions, and then we sum over all possible successor states, and we multiply the probability of moving to the successor state, given that we performed the action A, and then we multiply that by the previously computed probability for the successor state, so for S prime. So this is a approximate iterative solution technique, but as we can see, these probabilities are increasing, and they converge to the minimum probabilities. For max, it's almost the same. Obviously, we now do a max over the available action, and the only other change is here, and here it's those states where the maximum probability of reaching the target is equal to 0. So we can view this as a fixed point computation, similar to as for DTMCs. So for example, in the minimum case, we can consider the function that goes from probability vectors to probability probability vectors, where it returns 1 if the state is in the target, 0 if the probability of the minimum probability of getting to the target is 0, and otherwise we do the same thing as previously. We take the minimum over all actions, and then the probability of moving to a successor state multiplied by the previous, or the probability value in y. Now, if we let x 0, if we let the 0 vector be the vector of all zeros, and the n+1 vector be given by this function applied to the nth vector, then we have that this is we end up with an increasing sequence of, these are pointwise increasing sequence of vectors, and they converge to the minimum probability of reaching the target. And this is actually the unique fixed point of this select function. And the case for maximum is the same. All that we change here is that this changes to max, and we take a maximum over the available actions. So let's now apply these techniques to an example. So let's consider this MDP here. So here we only have a choice in state. We have a choice in state S 0. So there's this distribution here, where we go to S2 with probability 1/2, S3 with probability 1/4, and we stay in S0 with probability 1/4, or with probability 0.1, we go to S1. While in S3, we've got a non-deterministic choice between going to S2 with probability 1 or staying in S3 with probability 1. So I've omitted the action labels just to keep things simple. So let's consider value iteration, where we want to find the minimum probability that we get to S2. So our target is SM2, and what states is the minimum probability of getting to S2 equal to 0. Well, that's only S3, because in S3 we can just choose to take this self loop over and over again, and then we will never get to S2. So let's have a look at this. So we've got S min greater than 0 is S0, S1, and S2, and S3 isn't in the state as I've just said. The minimum probability of getting to T is indeed 0. So let's have a look at the probability vectors that we get. So in the 0th case, S1 and S0 and S1 are 0, this is the 0th case. S2 is 1 because it's the target, and S3 is 0 because the minimum probability is 0. So then in S0, we take the minimum over this choice here and this choice here, while in S1 there's no choice, so we just have this one update here, and this yields these probabilities here. Then if we apply it again, then we get these probabilities here, and if we keep going, then we'll see that we eventually converge to the probability for S0 is 2/3. For S1 it's 14 out of 15. Obviously it's 1 for S2 as that the target, and obviously it's 0 for S3 as the minimum probability, as we've seen, is 0. So we can then extract what the minimum strategy is. So if we see here, we see that it's this our distribution here that yields the value to thirds. So this is the optimal thing to take if we want the minimum probability. And as I've said, if we take this self loop, then the minimum probability of reaching the target S2 is 0. Obviously, if we took this one, then we'd get there with probability 1. So therefore, this induces this our DTMC, which yields these probabilities as well. So now let's go on to the second approach, which is based on linear programming. So here, this is the optimization of a linear objective function subject to a number of linear inequalities and equality constraints. And there's many standard solution techniques for such things, such as the simplex ellipsoid method and the interior point method, to name just a few. So in its general form, we've got a number of variables. Let's say we've got n variables x1 up to xn. Then we want to maximize or minimize some linear combination of these variables. So c1 up to cn are like constants, and so we want to maximize or minimize this sum, and then we have a number of our constraints. So we've got a number of inequalities here, and again, the A's and the B's are slight constants, and we can consider this in sort of matrix and vector form, in that we want to maximize or minimize C times X subject to some matrix times X less than or equal to some constants B. So let's see how this works for minimum reachability probabilities. So actually, minimum reachability probabilities can be computed as follows. So as for value iteration, we set the values equal to 1 if we're in the target set of states. Is obviously then the reachability probability is 1, we're already there, and it's 0 if the minimum reachability probability is not greater than 0. And we've already seen how to compute this set of states. Now, for the remaining set of states, so let's call these set S question mark, as we don't know the probability yet, then this can be obtained as the unique solution of the following linear programming problem. So here, we want to maximize the sum of the variables xs, and it's subject to the constraint xs is less than or equal to the sum. So these are over all of the states in the S question mark. So that, notice this is over all available actions in state S. So for any available action A, it's the sum over S primed. The probability that if we take A, we go to S primed, then multiplied by the value for S primed, and then we also sum. This is the probability when we're in S that we reach the target in a single step. Okay, so that's for minimum, and then all that changes for maximum is, instead of doing a maximize here and a less than or equal inequality here, we get a minimize here and a greater than or equal equality here, and that's all that changes. There is one other change, obviously, in that we have S max greater than 0 as opposed to S min greater than 0. Okay, so let's see this in practice. So let's first do a case of min. So here, if it's minimum, as we've seen here, S3. So first of all, so this is the target. So here we set x2 to be 1. S3, we can do this loop, and so here, the probability, the minimum probability of getting to the target is 0. So we set x3 to be 0, and then we've got what we're left with in S question mark is x0 and x1. So we want to maximize the sum of x0 plus x1 subject to our constraints. So first, for this choice here, this is x0 is less than or equal to x1, and then for this choice here we end up with 1. So this is x0 is less than or equal to 1 quarter times x 0, because we get back to s 0 here. This is 1 quarter times 0, so it isn't here, and this is 1/2 times 1, or 1/2. And then for x in state s1, for x1 we get 1/10 times x 0, then plus 1/2 times x1, and then 2/5 times 1 as we've reached the target. Now we can simplify this a bit, so we can take the x 0 here over to the other side, and the x1 here over to the other side. So we then get 3/4 times x0 and 1/2 times x1 here. And then we can move the 3/4 over to the other side and the 1/2 over to the other side. And we end up with x0 less than or equal to 2/3, and x1 is less than or equal to 1/5 times x0 plus 4/5. So let's have a look at these our constraints. So it's like the white area that satisfies our constraint. So this is where x0 is less than or equal to x1. This is where x0 is less than or equal to 2/3, and this is where x1 is less than or equal to 1/5 times x0 plus 4/5. So we want to maximize the sum such that all of these are satisfied. So let's look at when all of these are satisfied. So that gives this white area here. So all that I've done is I've combined these into one single graph, and then that leaves us with this white area here. And then we want to maximize the sum, so we find that the maximum is here, and we get the solution of 2/3 and 14 over 15 corresponding to what we found with value iteration. So we have that x0 is 2/3, x1 is 14 over 15, and then we had x2 is 1 and x3 is equal to 0. Okay, so just to give you just to show that we do end up with the same answer, this was the answer that we found through the linear programming problem, and in red I've shown the values that are computed by value iteration. Okay, so finally let's go on to a case for max. So now let's look at the maximum probability that we get to the target. So here again we've got x2 is 1. Now there aren't any states, so this should be s max, so apologies for that, but there aren't any states for which the maximum of getting to here is so both S0, S1 and S3 all have probability greater than 0 of reaching the target in the maximum case. As now in S3 we can always take this transition here. So for S0, S1 and S3 we get these equations here. So these three here are similar to the same as before, but we've got that the arrows are the inequalities are the other way around, and now x3 is not equal to 0, so we've also got this here. And then for state S3 we've got the two odd choices here. So here if we choose this one, we've got x3 is greater than or equal to 1, since we've reached the target here, and this is a self loop, so this just says x3 is greater than or equal to x3. So if we rearrange these, then we can simplify it to get these equations here. So if we first just look at x0 and x1, so the first equation here, this corresponds to this white area here. Here we want x0 is greater than or equal to 1, so none of this area is included, and this is the final case here. So it's this white area here is where x1 is greater than or equal to 1/5 times x0 plus 4/5. So if we are combined, then we take the minimum, then we find that there's only one feasible solution, and that's when x0 and x1 is equal to 1. Okay, so we've got the values for x0 and x1. So what about x2 and x3? Well, for x2, so we know it's like 1 because it's like the target state, and then we also know that x3 is greater than or equal to 1, and it's a probability, so it's equal to like 1. So in so this is so the maximum memoryless adversary. So in S0, it chooses this step here, and in S3, it chooses this step here. So this yields this our DTMC here, which also has in each state, so the probability of getting to S2 is indeed it's like 1. Okay, I'll only briefly go over how policy iteration works. So this is in value iteration, obviously, we iterate over the probabilities or the values, while for policy iteration, we iterate over the strategies or adversaries or policies. So we start with a arbitrary memoryless adversary or strategy, then we compute the reachability probabilities for that strategy, and then we try to improve that strategy in each state. Is there a better action that yields a higher probability of getting to either target? And if there is, then we change to that action, and we keep doing that until we can't improve the strategy any more. And this will terminate because there's only a finite number of memoryless adversaries or strategies. Okay, so just to mention, for more general probabilistic properties, for example, one can compute the minimum and the maximum probability of that an LTL formula is true. And how this works is we first need to compute the problem into just maximum probabilities. However, we can do this by using the fact that the minimum probability of satisfying some LTL property psi is equal to 1 minus the maximum probability of satisfying the negation of psi. And then similarly to DTMCs, we need to generate a deterministic Rabin automata for psi, or for not psi if we were interested in minimum probabilities. Then we construct a product MDP, and then we have to identify what are called accepting end components in this product. So a end, our component here is a set of states such that there is a strategy under which one always remains in the set. So that with probability 1 under that strategy, we stay in that set, and we also require that under that strategy, every state in that set is visited infinitely often with probability 1. And then we can compute the maximum probability of reaching these accepting end components. Okay, so it's just a quick outline of how it works, but it's the fundamental part is that we need to be able to compute maximum reachability probabilities. Okay, so one last thing just to say about our complexity of this. So if we use linear programming, then this can be solved in polynomial time, for example, using the ellipsoid method. And for the qualitative part, then this is linear in the state space. So we can introduce also reward structures for MDPs here. So here we can either have record. This is similar to DTMC, so we can have the reward accumulated in a state, or the reward accumulated when performing a certain action in a state, and then we can compute the minimum and maximum expected cumulative rewards before reaching a target. And the solution methods are similar to that I've just shown you for probabilistic reachability. Okay, so that completes this set of videos. So there's many other areas to our probabilistic systems, and I just thought I would focus on two of the fundamental models. So that is DTMCs and MTPs, and on the fundamental properties of probabilistic and expected reachability. Okay, so thank you.